Thanks, Chris. Okay, well, I think most of you have come back, so that's good. Quantum wasn't too indigestible. And judging from the questions I just got, it's pretty clear that most of you are on the message. In actual fact, I find that it's the questions my students ask that tells me whether or not they're understanding it, rather than the answers to the questions that I pose them, usually. At least that's true of the best students anyway. Okay, so this is lecture number 2. Let me just quickly revise a couple of things, just to situate where we're starting. As I mentioned in the last lecture, quantum theory tells us that the universe at heart is irreducibly random. At least that's what quantum theory says. May change one day, but at the moment, that's what we're stuck with. That is, even if you know everything there is to know about a particular system, there is always one measurement, the results of which are completely uncertain. Just in the start of this lecture, people were asking me about single photon states. There's a good example. If I have a single photon state, which are hard to make, I'll come back to that in a minute. A single photon state is one for which the intensity is absolutely certain. 1 photon per second coming towards or 1 photon per some unit of time coming towards the detector. But the phase, the optical phase, the phase of the electromagnetic field associated with that single photon is completely random. So the average electric field of a single photon is 0, but the average intensity is not. And that's a little puzzling. That's why it's such a non-classical state. The flip side of this complete uncertainty is also certainty. If you know everything there is to know about a physical state, then there's always at least one measurement which is completely certain. In the case of a single photon, it's the intensity. You always get 1 every time you measure it. So it's the way in which these two things cohere in a quantum state that makes quantum mechanics such a puzzling description of the physical world. And we saw some consequences of this. We saw that the way probabilities enter in order to guarantee this certainty and uncertainty cohering in the same quantum state is that there's a deeper level below probability. We don't have a good word for it, so we call it probability amplitudes, which when we square them, we get the probabilities. And it's probability amplitudes of one kind of measurement determine the probability amplitudes for every kind of measurement. If I give you the probability amplitude for single photon intensity measurements, number measurements, you can immediately calculate or demonstrate that the phase is completely uncertain. If I give you the probability amplitudes to find the position of some particle, you can immediately calculate the probability amplitudes to measure the momentum of the particle. And that's the way the theory works, and that's why a list of probability amplitudes for any one measurement is a state, because it completely determines the statistics for any measurement you care to make upon it. Okay, so this is what we came to at the last lecture. We spent a lot of time talking about single photons on beam splitters, and a 50-50 beam splitter. Classically, it just splits the amplitude of the field, so half the intensity goes one way, half the intensity goes the other. But we turn the intensity right down, so we're at this Einstein limit, where most of the time no detector goes off, but every now and then either one or the other detector goes off, but never both. And it's completely random whether it's the upper detector or the lower detector that actually goes off in a given trial. So it looks like a coin toss, but we saw, just by forcing it to make a second choice on the beam splitter, that is not like a coin toss, that there's this deeper level of probability amplitudes that's describing what's going on. And so the word qubit, quantum bit of information, was coined by Ben Schumacher back in the 90s to try and distinguish this kind of binary digit, random digit, from a classical one. So in this lecture, we're going to stop just being mystified and puzzled about quantum mechanics. We can go on like that forever, if you like, and some people do. But after a while, all the jokes about Heisenberg and dead cats and all the rest of it begin to pall a bit. So let's not do that. Let's not get mystified. Let's just accept the fact that this is the way the world is and figure out what we can do with it. What sort of useful technology does this enable us to implement? Now you might think, well, if the world is irreducibly certain, this must just place some limit on our technological capabilities. Sooner or later we'll hit the quantum level and all things will fall to bits and we won't be able to, bits, not in the sense of qubit, fall to pieces perhaps would be a better way of putting it, and we won't be able to proceed further. It was originally thought that Moore's law would eventually hit this limit. Moore's law, you may know, is that computing power doubles every 18 months or so. And the only way for that to happen is everything has to get smaller. And so the transistors have to get smaller and smaller and smaller. Eventually get so small, they're about the size of a single atom. And then you have to worry about quantum effects, and it was thought that these would derange things. For a long time, that was where things were stuck, but it was realized by somebody called, well, a number of people actually, Feynman originally, but David Deutsch in particular, that rather than restricting our capability to build computers, quantum mechanics will enable a completely different kind of computer to be built, one that will be vastly more efficient than any classical computer. So that's one example of a quantum technology, but I want to look at some other ones in this lecture as well, particularly high-precision sensors and energy harvesting devices, of which photosynthesis is a good example, something we've learned very recently and I still find extremely surprising, that after 3 billion years of evolution, nature hit on a quantum feature that gave a slight improvement in photosynthetic energy transfer. So, let's begin. So I said that we can encode this quantum state as a list of probability amplitudes. So here's a quantum state which is definitely going down. I've lost my pointer, but never mind. So I put a 1 in the first entry and a 0 in the second. So I square 1, I get 1. Oh, there it is. Thanks. So that's a state which is definitely going down. That's a state which is definitely going up. And on this side, these get replaced by 1 on root 2 and 1 on root 2 in this case. So when I square them, I get a half. So we talk about superpositions because we don't have any good way to talk about what this qubit means. It's not really a coin toss. It's not either heads or tails. I just don't know which. So the best we've come up with is superposition. And we always have trouble in trying to use ordinary language to talk about quantum states because we don't live in the quantum world very easily. It takes a bit of effort to control the world at the level of probability amplitudes, and we need a technology to do that. So let's see how that can help. So I'm going to just get rid of all these brackets. I'm just going to say if it's definitely 1 going down, then after it's a superposition of 1 and 0. What I mean is that there's still a 50-50 chance of finding it going up and finding it going down. In this case, remember, we had to put a minus sign on the reflected part for it to go down. And that's, to go up. 0 is going up. And that's to keep track of the fact that the beam splitter is time reversal invariant, and distinguishable states at the input must be mapped to distinguishable states at the output. The probabilities are both half. That doesn't distinguish them. But probability amplitudes, which enables me to put in a minus sign, enables me the ability to make these physically distinguishable. And that's a deep principle of why we need probability amplitudes in quantum mechanics to guarantee time reversal invariance. So you can see that if I think of this as a binary digit, what I've suddenly done is take a single binary digit and put it into a superposition of 2 binary digits, and likewise. So let's have 2 beam splitters. So now I have 2 beam splitters, and now 1, 1 goes to 1, 1, 1, 0, 0, 1, 0, 0. You can just work that out for yourself. This is very much like tossing 2 coins. If you remember the example I gave in the last lecture, if you toss 2 coins, you can get tail, tail, head, head, tail, head, head, tail. I need 2 binary digits to encode 4 possible outcomes. But here they're being encoded at the level of probability amplitudes. So in some sense, this coding is simultaneously present to superposition across all these outputs here. If I actually go in and measure it, I get one or the other. I only get a click there, a click there, a click there, or a click there. But if I don't measure it, I just let it go. Then they're all simultaneously present. So I could keep going on that. I could have n physical qubits to encode 2 to the n binary numbers. So this can get pretty big pretty fast. With 100 physical qubits, that is 100 photons and 100 beam splitters, I can encode 2 to the 100 possible binary strings in that representation I just described. We call it a physical coding. So 2 to the 100, can anybody tell me what that is roughly? Maybe it's easy to convert to base 10. It's about 10 to the 30. That's a pretty big number. So even with just 100 photons and 100 beam splitters, which as you'll see shortly is easily within technological reach, we can start encoding vast numbers into this device. But what's the point of that? Okay, well, this is what David Deutsch pointed out. He said, one way to make use of this is if you have a particular calculation where you want to run the machine on every possible input. So we're going to encode all our inputs as binary strings. And we don't really care what the value of the function on any particular binary string is. All we care about is some property of that function. For example, you might want to know, is it constant? No matter what input I put in, the function always gives the same number, 1. That might be one thing. Well, it would be pretty easy to check that just after a few trials. You wouldn't have to try very hard. What about, is the function balanced? That is, it gives an equal number of zeros and ones. Well, you might have to run it a few times before you're convinced that it's giving ones half the time and zero half the time. But there's one kind of calculation which is really hard to do, and that is finding the period of a function. And this gets to the question of efficiency. So let's suppose our function repeats after a certain number of inputs. So if I put in 1, it gives 1. If I put in 2, it gives 2. If I put in 3, it gives 3. If I put in 4, it gives 4. If I put in 5, it gives 1 again. So there's just modular arithmetic. In that case, I only had to run it 5 times to see that it was repeating. But let's suppose its period was a 128 binary digit number. You're going to have to run this machine many, 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 many times before you can convince yourself of what the period is. You keep going and going and going and going. Finally, it repeats. You think, but maybe it was just an accident. Let's do it again. So off you go again. It's repeated. So those sorts of calculations are very inefficient. And this question of efficiency goes to the core of why a quantum computer is useful. So the key thing about a quantum computer is a physical device that's processing this coded information fully quantum mechanically. Could it operate more efficiently than a classical computer? Could it do things quicker? And this was Feynman's original question, and it was the question that Deutsch answered in the affirmative. So what does this mean? Well, I hadn't enough time to go into the theory of computing. It's based on this key principle of computer science, which some people refer to as the kind of Newton's law of computer science, the Church-Turing thesis, that, it defines a computable function as one that can be computed by a kind of idealized computer, a so-called Turing machine. And a computable function is one that's computed by a universal Turing machine. And all the computers we have are, in essence, universal Turing machines. This kind of thing would be incredibly slow, the one that he described, if you actually built it to erase and print ones and zeros on a piece of paper. But it's no different, the basic operations are no different to what is operating in this laptop here. However, even those sorts of things, for finding the period of high period functions, are not very efficient. So the question is, how many steps are required to compute a function? How many operations per second? That's the first question. The second is, how does the number of steps depend on the size of the problem? So if it is proportional to the size of the problem, so let's suppose the size of the problem requires me to specify a 100-bit number. Then if I need of the order of 100 steps to compute the function, that's okay. If I need of the order of 100 squared, that's okay. In fact, if I need of the order of 100 to some power, that's generally okay. But if I need of the order of 2 to the 100, I'm in big trouble, because I only have to add 1 extra digit, and it takes twice as long to run. If I add 2 extra digits, it takes 4 times as long to run, and you can see that this will quickly kill you. So these sorts of problems where the number of steps scales exponentially with the size of the problem lead to inefficient computations. So here's a good example, finding the prime factors of a large integer, which you can write out in binary form. You can check, see if that's right. You can always check if it's even or odd just by looking at the last digit. The rest of it's a little more hard to work out, but you can do that over the lunch break. So how would you find the prime factors? Well, you divide by 2. That was pretty dumb, because there's a 1 here. That means it's odd, so that was silly. So you divide by 3, and you keep going until finally you get to a number that divides it, 541. And so you can see this is not terribly efficient. You're going to need of the order of square root of that number steps to actually find the prime factors. So if I'm using base 10, I add 1 more digit. Square root of 10 is about 3. I need 3 times as many steps just by adding 1 digit. So these sorts of things are hard. Finding the prime factors is hard. Of course, once you've got them, anybody can check on their phone or whatever whether they are the prime factors, just multiplying together. So these sorts of functions that are hard to do one way and easy to do the other are the really difficult ones for a conventional computer to do efficiently. And because of the difficulty of that particular algorithm, that particular step is built into all the public key encryption systems, at least most of the ones that we use on the internet for encoding credit card information and personal information. There's something called public key cryptography, which enables you to easily encrypt information, but hard for anybody to decrypt it. It's easy to multiply 2 prime numbers, but it's very hard if you're given the composite to figure out what the prime factors are. So I won't go into the details. You can Google it. You'll find lots of discussion on the web about public key cryptography. It was discovered secretly by mathematicians at GCHQ, the Security Intelligence Agency in the UK. They couldn't tell anybody about it because they were, spies basically. It was later discovered in the outside world by Revista Shamir in Edelman, and that was known as RSA. And it wasn't until much later that the guys who discovered it first, but had to keep quiet about it, were able to say that, well, actually we found it first, but it's too bad. But the key step in all of these things in finding a factor is to find the period of this modular function. So here's a good example. We have some function which is x to the a, mod n. So if n is some huge integer, if x is 5, then x to the 1 mod 5 is what I just gave. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes back to 1 again. X squared mod 5, well, you can work that out for yourself. But you can see these are period. They just repeat. But if this number n is really big, as it would be, because this would be the integer you're trying to factor, then you're going to have to run this machine many, 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 many times. And so as long as n is big enough, and as long as public key crypto systems, the prime seed is big enough, no computer on Earth will do the calculation before the universe comes to an end. And if you're worried, just add a few more digits. So you can always get around it. But Peter Shaw, having read David Deutsch's paper on quantum computing, thinking about it for a while, he was a computer scientist at that time working at AT&T. Can't remember where he moved to. Maybe it was Princeton, I'm not sure. Discovered a quantum algorithm. That is an algorithm which, run on a quantum computer, would find the prime factors very, very efficiently indeed. In fact, exponentially faster. So this means there's an algorithm which is literally unimplementable in the classical world. It only can run if there is a quantum computer, and because the world is quantum, we know that quantum computers could be built. So the hardware matters in a fundamental way. There's a fundamental link here between a mathematical property, an algorithm, and the way the world is built that enables us to do some calculations more efficiently in the quantum world. So that was a bit of a worry, of course. When the spies discovered that someone might build a quantum computer and crack all their codes, they got a little anxious. Even better, they got very generous with their funding. So they started putting a lot of money into quantum computing. And so this huge investment generated a great deal of experimental activity. And much of what we can do today in quantum technology started because of this huge effort that went into building quantum computers. We don't yet have a quantum computer. It turns out not to be easy. But we're certainly much further ahead than I would have ever expected by this point. So there's a lot of different technologies I could talk about. There's a couple being built here at the University of Sydney based on spins in gallium arsenide, which you heard about from Professor Riley last week. Michael Biersick here at the University of Sydney using ion traps. One of the most promising candidates based on superconducting quantum circuits. I don't have much time to talk about that. But the other one, which we're implementing at the University of Queensland and many others, is based on photons. And I'm going to talk about this example because that's where I started yesterday. Single photons, we've already seen how just 10 photons and 10 beam splitters can encode at a number which is 2 to the 10, about 1,000. And 100 beam splitters enables me to encode astronomically, well, not astronomically large, but 10 to the 30 is getting pretty astronomical. So here's what they look like. There's some fundamental layer of stuff which could be optical fibers, and here's some optical fibers all being mixed together like a beam splitter. There's some polarizers I can put in, there's some sources here to make single photons, and then there's some detectors at the other end. And the whole trick of building a quantum computer out of this thing is figuring out what to put in here, what sort of circuit to put in there. To do that, you go up to this mathematical level and write down what's called a quantum circuit, which is basically a sort of machine language code for quantum computing. And on top of that, this tells you what the kind of big sort of transformation from input to output you need to implement. Certainly more than just one beam splitter now. It's lots and lots of beam splitters and all sorts of other things sitting in there. Now, what could you do with that? Well, it wasn't entirely clear. It was thought that you'd have to have pretty complicated things sitting in there to do factoring, or in fact to do anything that would be difficult to do classically. But Aronson and Arkhipov discovered just a few years ago that almost anything is too hard for a classical computer in that box. And they showed that predicting the probabilistic results of some given quantum mechanical experiment of the kind I just described, with single photons and beam splitters, lots of photons, lots of beam splitters, all bouncing every which way like some big sort of billiard game for photons, to predict the probabilities of those outcomes In polynomial time, that is in something that scales with the number of steps raised to 1, the number of step scales is the size of the input to some power. That turns out not to be possible on a classical device, unless a classical device can factor large integers as well. Now, we're not absolutely sure that someone can't factor large integers. It's just that no one's figured out a good algorithm to do it yet. But we're pretty confident that factoring integers is a hard problem. Certainly in the classical world. In the quantum world, it's not. It's an easy problem. And this is a whole other class of problems of predicting these probabilities. We worked out a couple yesterday. They were pretty easy. I took 1 on root 2 and squared it and got a half. That wasn't too bad. But if I've got hundreds of beam splitters in there with hundreds of photons, then keeping track of all these minus signs and 1 on root 2s and all the rest of it is pretty hard work. And they don't all have to be 50-50. Some might be 1/3, 2/3. So 1 on root 3, root 2 on 3, and so on. So keeping track of all that is really hard. And in fact, there's one particular set of problems which is called finding the permanent of an n by n matrix, which is really hard, which these machines can do really easily. So I don't know, has anybody heard of a permanent? Has anybody heard of a determinant of a matrix? Okay, basically a permanent is a determinant with all the minus signs changed to plus signs. So you might think, well, that doesn't sound like much of a change. And determinants are not that difficult to work out. Okay, they're a bit boring, but there's a pretty straightforward algebra for doing it. But it turns out permanents are much harder. Computer scientists call this sharp P complete. It's kind of surprising, but just try it. Write down a sort of 6x6 matrix and work out the permanent. You'll find that it's pretty tough. But it turns out you can build a photonic processor of the following kind, of a bunch of beam splitters at the input, bunch of single photons going in, and as long as you have twice as many beam splitters as photons, then predicting the probabilities of the outcomes here is as hard as computing this permanent. In fact, it's given by a permanent. You have to actually calculate a permanent, which is massive, 2 raised to the power of the number of photons that have gone in. But this device, you just run it a few times and sample the probability and you're done. So it's probabilistic, but it's at least achievable in a time that's much, much faster than anything that a classical computer could do. So my colleagues at UQ built one of those. The essential ingredient in this device is what I mentioned yesterday, this absolutely crucial quantum interference when you have 2 photons simultaneously on a beam splitter, on a 50-50 beam splitter like this. If it was a coin toss, you'd expect a coincidence count 50% of the time. 1-1. If these go off together, it should happen 50% of the time. But in fact, it never happens because of the cancellation of the amplitudes for the 2 ways I can get a coincidence, both reflected or both transmitted. And that's the key that makes this machine capable of computing permanence very efficiently and why it's hard to do it classically. So the experiment was published earlier this year in Science, a famous journal of the American Association for the Advancement of Science. It looks something like this. They didn't actually use light propagating in free space. They didn't even use optical fibers. What they did was they got a block of glass and they took a laser and focused it down inside the glass and etched little waveguides for light. So you may have seen ornaments like this. You can etch pictures into blocks of glass. In fact, sometimes you can find these booths that will sort of take a picture of you and etch it into a block of glass, and you can show your mum or something or other. So that's what they did. They took a laser and focused it down inside the glass and wrote these waveguides. And they, depending on how they overlapped, they could have a 1/4 beam splitter, 1/5, and so on. All sorts of different transmittivities and reflectivities through this device. And by changing the length, remember in the description of the LIGO experiment, as we changed the path length, we inserted some extra probability amplitudes, some rotations. They could do that too. So they just built this thing in a big block, so it didn't move much. They just got it back from the manufacturer and put it in the lab. Now they've got to put some single photons in. How do they do those? Well, the trick is to use, remember yesterday I was discussing this way to produce twins, photon twins. So they produced at random times, but they're always produced together. Green photon goes in, 2 red photons come out. They're produced at random times, but if I can detect one, I know for sure the other one's on the way. So I can make conditional single photon sources this way, and that's what they did. They had these big multiplex down conversion devices to generate lots of single photon sources. So single photons come out, then they input them to here. You see there's 3 going in, there's 6 outputs, so there's twice as many photons as there are outcomes. That's what we want. And they were able to demonstrate this very simple permanent evaluation. Now for 6 it's not too bad, but If we had much better single photon sources, and that's coming, they'll be developed over the next couple of years, there's nothing to stop us from writing in thousands of these waveguides into glass. Hundreds of thousands, in fact. The real problem is getting enough single photons, but that technology is underway. So building very large permanents. Oh, well, that's nice to know. It's one of my students updating a paper that we're writing. Sorry about that. I thought I turned it off. Okay. So they built that device and it works just fine. It's called the boson sampling problem. Photons have spin, integer spin. They're called bosons. Electrons have half integer spin. They're called fermions. That's not too important. It's surprising. Generally, people thought that it would be the fermions that would be hard to simulate in these sorts of experiments. It turns out it's the bosons in this case. Fermions are easy for this sort of problem. Okay, so that's one example. So quantum computing is one technology that we can see how to do now. It's going to be hard. Little way to go. No one's built a factoring engine so far as I'm aware. The real effort's going into quantum simulation, building machines that can simulate drug design and quantum chemistry. It's clear that if you want to do ab initio, that is, first principles calculation of the ground states and the lead-level structure of some complicated molecule like caffeine, it's not easy to do on a classical computer. Quantum chemists have developed clever algorithms for it. But we now know from the work of a group at Harvard and people at the University of Queensland that even if you have, say, a few hundred qubits, you could start doing first principles computations of very complex molecules with interesting biological importance behind them. So a lot of the effort is now going into building small quantum computers to do quantum chemistry simulations. That's pretty exciting. Oh boy, sorry about this. I haven't backed up. Oh god. Okay. So there are many other kinds of technologies that we're going to talk about. So the objective again is to build functional engineered quantum systems that exploit quantum coherence, just like the quantum computer does. And quantum coherence, as I said, is this hidden layer of the physical world. It's not that easy to control it, but we're learning how to do it. And there are many other technologies that we can build based on. So the idea here is to build artificial devices, artificial systems with a predefined kind of quantum behavior to them. For most of the history of the 20th century and the early part of this century, quantum physics was all about finding quantum stuff and studying it. It started with atoms, trying to understand how atoms had the properties they do, that is a discrete spectrum. Understanding photons and beam splitters, that's fine, we could do those experiments. But now what we're going to try and do is to engineer complex physical systems, certainly many, many more than one atom, 10 to the 23 atoms, with sufficient control over certain degrees of freedom that enable us to do interesting quantum technological feats with macroscopic objects. So in the good old days, people used to say that, oh, the division between the quantum and the classical is the same as the division between the microscopic and the macroscopic. There's absolutely nothing in quantum mechanics that says that. As far as quantum mechanics says it's written, the theory that you're given, it may not be entirely obvious to you when you first look at it. It doesn't say that apply until you have 20 atoms and then stop because it all falls to bits. The theory works fine. It just keeps going. In fact, you could apply it to the whole universe. In fact, people do. Seems to be a bit ambitious from my point of view, but people certainly do. But there's nothing in the theory that says I can't keep making them bigger and bigger. In fact, we already know how to do that. So already we can build these so-called superconducting quantum circuits. So the key thing is getting sufficient control over probability amplitudes of more and more and more and more bits of stuff, and then getting exactly the kind of control you want to do some interesting feature. So these superconducting quantum circuits achieve that because if you put certain metals at very low temperatures, they lose their resistivity and they become completely reversible. They're not, it's like trying to do experiments with photons. If some of them got lost and absorbed, or there were thermal photons being emitted all over the place, you'd never be able to keep track of what was going on. Fortunately, at optical frequencies, the world is pretty cold. There are no thermal photons out there. It's just as well, otherwise it'd all be fried. If you were a bit closer to the sun, it might be a bit different, but we're pretty safe. But in these devices, they operate quantum mechanically just by putting them into a very good fridge. But there's nothing microscopic about it. You can see these things with the naked eye. Okay, they're not that big. So what this is it's some metal deposited onto a substrate, often sapphire. And here's a big spiral of metal. So there's a wire running up the top here. It's actually a little coaxial cable. Here's a big spiral. That's just an inductor, just a big loop of wire, just like an inductor. It's like a solenoid, but squashed down onto a spiral on the surface. And then it's connected over here to a capacitor. Now, the interesting thing about this capacitor is the head, one plate is a little drum head suspended 50 nanometers above the surface. It's quite a challenge to build, but the technology for doing it is now perfected. They can do this routinely. So that little drum head can vibrate up and down. And you know that the capacitance, or you probably should know, capacitance depends on the distance between the plates. And so if you're modulating the distance, you're modulating the capacitance. So here we have an LC circuit with an inductor and a capacitance, and the energy will slosh backwards and forwards from magnetic energy to electrical energy and so on at some frequency, determined by 1 over the square root of the capacitance times the inductance. But if I modulate the capacitance by vibrating this drum head, I'm going to modulate the frequency. And so I have a device where the frequency is being modulated by this vibrating drum head. Now here's the extraordinary thing. It's not just the circuit that's quantum mechanical. It turns out that the vibrations of this drum head are also have to be described by quantum mechanics. So there's, the order of 10 to the 16 atoms in there, and it's this entire flexing mode of the drum head that's being described quantum mechanically, and in fact behaves quantum mechanically. You can cool it, in fact, down to the ground state of that flexing degree of freedom. So that's quite remarkable, and quantum mechanics just keeps working. The quantum theory of these circuits you actually can already do. If you've done a little bit of circuit theory, who's here heard of Kirchhoff's rule? So it's the rule of currents being summed into a node, the sum of voltages around a circuit is zero. That's all you need to do the quantum theory of these circuits. That supplemented with this uncertainty principle, and you're off. You can start computing probability amplitude. In other words, you don't have to solve the Schrödinger equation for all the superconducting electrons, Cooper pairs inside this thing. And this is quite remarkable. And so that's why I say these devices are described by quantizing a collective macroscopic degree of freedom, and it works fine. Now, the idea of doing this for superconducting circuits was pointed out by Tony Leggett back in the 80s, who got the Nobel Prize for this. He's a theoretician at that stage, working in Sussex in the UK, now works in the United States. He pointed out that you could do this effective quantization, figure out what the key macroscopic variables are that you can control, in this case current and voltage, and quantize them directly. And it was highly controversial at the time, until a bunch of people did an experiment, and he was right. He gave exactly the right spectrum for the energy eigenvalues of this circuit. And so it then took a long time for people to get the technology right to build these things so they behaved the way we wanted them to. That is, to get the right control over exactly the probability amplitudes for current and voltage. Although typically it's charge on the capacitor and flux through the inductor that we control. So that's one example of an engineered quantum system. The other kind, which I'm going to spend most of the talk now discussing, are optomechanical systems. So remember when I was discussing the LIGO experiment, I said that the big problem that enforced the Heisenberg uncertainty principle, you want to find the relative displacement of two arms, of two mirrors in a Michelson-Morley interferometer. But the individual photons kicking the mirrors around disturb them as much as a gravitational wave would coming through this device. And so cranking up the power to get better and better sensitivity is a bad thing to do, because eventually you just have this source of noise heating up the mirrors. So that tells you that I can couple light to vibrational motion easily. And optomechanics is a whole new technology based on that idea. So the idea is to build little vibrating mirrors. Here's one from Aspelmeyer's group in in Vienna. And you can see they use sort of modern lithography techniques to etch out under here and leave this little beam suspended with these little weak supports. So it's just vibrating up and down. And again, it turns out that all you have to do is elastic continuum, just elastic mechanics of that, purely classical theory down to Schrödinger's equation, and just write down the quantum theory straight away. So it's vibrating up and down, and it's got a little mirror coating on it. So they can now put another little mirror above it and make a little optical resonator between those two. But now the light, just like in LIGO, can start to push that mirror around. So you get this coupling between the vibrations of a mechanical element and the light inside a cavity. Here's the kind that we're using at the University of Queensland. This is one from Kippenberg's group in Lausanne. What you do is you build a little sort of mushroom of silicon, zap it with a laser so it melts a little ring around the outside. This is like a little donut of optical fiber now. And light will just rattle around inside this ring, being totally internally reflected all the way around. It's called a whispering gallery mode. So if I bring in an optical fibre and just touch it to the side, I can excite an optical field to just go rattling around inside that little donut. Now again, the trouble is that this thing can flex, right? It can flex up and down like this, or it can develop a kind of sort of crown vibration around the outside, and that changes the size of the optical path length. And again, just like in LIGO, enables the light to couple to the mechanics. And again, it's the quantum elastic degrees of freedom of the whole thing that are quantum mechanical. And here's another kind. These are the ones that are really pushing the future for this. They're so-called photonic crystals. The idea is to take something like glass and drill lots of holes in it so that you modulate the refractive index in space. And this means only certain frequencies of certain wavelengths of light can propagate in the device. They're called photonic crystals. And modern optical fibres often have these sorts of holes written down the middle. And I think, has Tanya Munro spoken yet?
No, we did have a couple of talks.
Okay. Okay, so these are photonic crystal devices. So you can build little cavities in here where the electric field will just build up and get stuck and just sort of oscillate. But what's even more exciting is as the electric field builds up, it starts to strain the whole crystal structure and push it out and change the distance between all the holes that you've just drilled and change which frequencies are supported and which frequencies are not supported. Even better, it also modulates the ability for sound waves to propagate in this thing. That is, the ability for vibrations. So you can restrict both the electromagnetic field propagation and the propagation of sound. And just like photons are the quanta of light oscillations, we call the quanta of vibrations phonons. So again, the elastic degrees of freedom of this vibrating thing are now controlled by drilling these holes in it. And this gives extraordinarily strong coupling between vibrational motion, in this case it's stretching this thing, and the optical field. So you can build entire phonon circuits in this device. Devices that do quantum computing by coupling vibrations of mechanical elements, just the elastic response of this thing, to its ability to support oscillating electric and magnetic fields. Even more remarkable is we can cool these things to the ground state. So here's the basic idea. This is a little bit of theory. If you have two mirrors like this, you know that it can support frequencies that are given by an integer times pi over the speed of light times the distance between them. You can fit in half a wavelength. You can fit in one wavelength. You can fit in 3/2 of a wavelength. And that's all that is saying. So now what's going to happen if this mirror moves is you have to modify that condition a little bit. So instead of n pi c over L, it's n pi c over x, where x is vibrating backwards and forwards. But that's really small. So I can expand it out to lowest order, and I get this coupling now between the position of the mirror and the frequency of the light in the cavity. So this is very much like frequency modulation in radio transmission. I have some frequency which I can modulate at some much, much lower frequency and use that to carry information. In this case, I can use it to cool the mechanical element. Just coming back to LIGO, we now can see how the radiation pressure force works. It's just given by that fundamental constant, which is omega c, the frequency I use over the length of the arm of the interferometer, multiplied by Planck's constant again, and the number of photons in the cavity. So if you really want to calculate the radiation pressure force, there it is. And the problem in LIGO is this NT fluctuates in one arm, because sometimes it's reflected and sometimes it's transmitted, so the force is jumping around all over the place. So the radiation pressure force per photon is that. You can check the units if you're worried. It comes out in terms of newtons. And here's how cooling works. It depends whether you drive the cavity at a frequency below that natural resonance frequency. It's called red detuning, push it to the red side. Or you put a laser in that has a slightly higher frequency than the cavity. And when you do that, you discover that the mirror either lags behind the intensity inside the cavity, or the intensity inside the cavity lags behind the mirror. So here's what happens. Here's my cavity. I fire in a laser, intensity starts to build up inside as it bounces backwards and forwards, but as it gets big enough, the radiation pressure force begins to push the mirror out. So now the cavity is detuned, so suddenly the light leaks back out again, and now the mirror has less photons to push it, so it comes back. Now it starts to build up again and gets pushed out. So it all now depends upon the relative phase of the intensity going up and down and the motion of the mirror. If I do it so that I'm on this side of this resonance peak. So this is the intensity of the light in the cavity. It's the usual resonance peak. It doesn't go to infinity because there's sort of light leaking out through the mirrors. So I don't know whether you've done these experiments where you take a harmonic oscillator and drive it harmonically, and you'll see the intensity builds up when you get it exactly on resonance. That's when you get the maximum. But over here you get a little bit, over here you get a little bit. But if you drive it way off resonance, you don't get much light in the cavity at all, much excitation of the optical resonator. But if you drive it on the so-called red side, it turns out the light is always pushing the mirror when it's trying to move the other way. So it's always trying to cool it, like that. But if you tune the driving frequency to the blue side of the cavity, it's 180 degrees the other way. So the light is always building up as the mirror is moving further away. So it gets hotter and hotter and hotter. Of course, eventually something terrible happens. It falls apart or breaks or goes non-linear or actually usually just melts. But cooling is good because this means I'm cooling a vibration, which means eventually I'll get down to the ground state. I'll suck out all these quanta of vibrational motion, these collective elastic vibrations, and just get down to the lowest possible state I can get to allowed by the uncertainty principle. I can't get down to zero motion because that would violate I can't get down to something that is literally going nowhere at no speed. I'd violate the Heisenberg uncertainty principle, but I can get down as low as I possibly can. And now people have done this. They've cooled these macroscopic devices down to the ground state. That's pretty cold. And in fact, there's nothing to stop you doing this for bigger and bigger and bigger optomechanical systems. So as I said, this artificial boundary that says the quantum to classical is the same as microscopic to macroscopic will certainly fail for these systems. There's nothing to stop us from doing this all the way up to LIGO. In fact, there's a group at MIT trying to do this for gram scale mirrors separated by meters. And what they'll do is put these big mirrors into a superposition of this one stationary, at least as stationary as it can be, quantum mechanical, and this one moving a lot, and vice versa. So that would definitely be a macroscopic superposition, and they're well on the way to doing that. Now, what gets interesting then, of course, is that the mass is no longer insignificant. It's getting pretty big. In fact, gram scale, if they're not too far apart, you're going to have to start worrying about gravitational interactions. And so for the very first time, we're going to be forced to try and think about the interplay between quantum mechanics and gravity. Now, this has been a subject that's been discussed forever, because people have been trying to quantize Einstein's theory of gravity since Einstein first proposed it, all with total failure for various reasons. And it was originally thought, okay, well, we're not too worried about total failure because they're only going to apply to the most extreme events in the universe. But it's beginning to look like it's going to apply to these things that are extreme, but they're definitely not, they're not black holes or anything too exotic. There's a few grams, a few centimeters, and you do start having to worry about gravitational gradient forces in the presence of quantum effects. But that's a whole other story. What can we do with these things in terms of applications? So I'm just going to talk about a couple now. This is one we're building at the University of Queensland. It's a very sensitive magnetometer. Now, why would you want to sense weak magnetic fields? Well, it's used in medicine all the time. There are these so-called superconducting quantum interference devices based on those superconducting circuits I just described, and you put them on, put cold ones on your head, and it can pick up very weak magnetic fields due to all the sort of circuits in your brain, and you can use these to diagnose various kinds of pathologies, such as epilepsy and so on. The trouble is, putting superconducting things in liquid nitrogen on your head is a little inconvenient, to say the least, not to mention expensive. So it'd be much nicer if we could do that with just room temperature devices. And we've now invented a way to do that by using these optomechanical systems. And the point is, if I do the detection purely optically, it can be done virtually noise-free, because, as I said, at optical frequencies, the world is pretty cold. So if I can detect weak vibrations or distortions of the size of this disk optically, I can do it extremely accurately. So the real question now is, how do I get magnetic fields to change the shape of that? Well, magnetic fields don't interact much with glass. I don't know if you ever tried to pick up a piece of glass with a magnet, but if you have, you'll know it can't be done. So what you have to do is put some goo on the top of that. So they've discovered there's some stuff which is sort of like black goo, that's the only way I can describe it, called tefenol, which they've figured out how to coat the top of this thing with. And the interesting thing about tefenol is in a magnetic field, it shrinks like that. So if you put this stuff on top of your disk, put it near a magnetic field, the whole disk sort of buckles up like that, or buckles the other way. And that changes the optical path length, giving you a measurement of the size of the magnetic field. and it all works at room temperature. You don't have to cool these devices down to get this to work, because ultimately all you're caring about is the light, which you can make extremely accurate measurements of at room temperature. So how well can they do? Well, they're already pushing the boundary with these superconducting devices. So that's where they started about 2 years ago. Just 6 months ago they're here, and they will certainly get down below the squids, or at least to the squids. And so needless to say, this is quite a valuable invention, and will now be spun off for future development. But it relies on the ability for photons to behave quantum mechanically as they rattle around inside that little optical donut, just like I described with photons at beam splitters. So that's one application of this quantum technology, taking a macroscopic, well, not that macroscopic, it's a little tiny, mushroom-shaped thing, a few microns across, but it's pretty big, 10 to the 20 atoms or something, cooling it down so it behaves fully quantum mechanically and enabling you to read it out optically, gives access to this new sensor technology. And this can be done in many different applications. One is to build an accelerometer, or something that can measure very weak forces. So I don't know how many people here have an iPhone. The makers of the iPhone were very smart. At some point they decided, wouldn't it be fun to build an accelerometer into the iPhone? So every time I turned it, the screen would adjust accordingly. So if you sort of rotate something, it feels this effective force acting on it. So inside the interferometer is something that feels, inside the iPhone is a little accelerometer that can detect these weak forces. Well, you can do much better with optomechanics. So they came up with a way of having a little wire stretched across here, coupled to this optical field running around the outside of this disc, so that as you push this thing, the wire starts to vibrate, and that modulates the light inside the disc as well. So this was a result published just last year from the group in Lausanne in Switzerland. Switzerland, showing how to make ultra-sensitive force measurements. They then went ahead with this group in Caltech using these sort of acoustic and optical crystal devices to build an even better accelerometer. This is what they look like. They operate at room temperature. They give incredible sensitivity to very, very small accelerations, so they will soon start turning up in phones. Then there's this really clever device to build a memory element. Basically what happens, we build this little optical waveguide. It's like a little tiny little bit of optical fiber, except it's not glass. But we dig a hole out, and so what happens is as the intensity in this ring builds up, it pushes on the walls, just like the radiation pressure force, until eventually it buckles. And it can buckle down or up, depending on which way you send in the light. And if it buckles up, it stores 1. If it buckles down, it stores 0. So you have this way of optically storing information in these things. And you can use these devices as a kind of frequency modulator between different frequencies, even between microwaves and optics. Now you might think, well, who cares about modulating between optics and microwaves? Well, in fact, mobile phone technology is all microwave technology. All the signals are passed via microwaves. But our communication systems that we use when we connect to the internet is all optical fiber. And at the moment, the only way to interconvert is take the microwaves, which is electronics, turn it into optics, bring it back up to electronics and back to microwaves. It would be just wonderful if we could just do that seamlessly. And these sorts of devices, these optomechanical devices that can couple a vibrating element, which could be both a capacitor plate in a circuit and a mirror for a cavity, give a direct way to interface microwaves with optics that will be incredibly fast and incredibly efficient, and will give us much, much faster routers for the future of the internet, all based on quantum optomechanics. But now let me finish with some fairly exotic thing. So let's, actually it's not that exotic. In fact, life on Earth depends on it. It's called photosynthesis. We've only just recently discovered it's exotic. So inside photosynthesis are pretty complicated big molecules, but inside those molecules are these pigments called chlorophyll. And basically they're little arrangements of molecular dipoles, electric dipoles, which when light hits them start to oscillate. And what will happen is when one starts to oscillate, it'll induce an oscillation in the next one, which induces an oscillation in the next one, and eventually the energy will start being passed around through all these chromophores inside a so-called antenna complex. And in the middle here is something called the reaction center, which I've tried very hard not to think about because the chemistry involves something more than hydrogen. So in here there's some magical chemistry that goes on that takes the optical energy, goes bang, 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 ends up here and produces something interesting. Typically it splits water, I can at least understand that, produces hydrogen and oxygen, but the hydrogen then goes off and starts producing carbohydrates and ATP and all the sorts of chemistry that you need for life. But when people started investigating it, they originally thought this was just some sort of random walk. The energy just jumped around like some sort of drunken person trying to find their way home. But it turned out that was way too slow to explain what was really going on. It's incredibly fast, the way in which energy is pumped through to this reaction centre, far faster than a random walk would suggest. So that kind of got interesting until finally they started taking these things out of the plant and putting it in a cold environment and doing spectroscopy on it. And they discovered that in actual fact it's very, very quantum coherent. It's behaving like a quantum random walk. And there was clear evidence for that. It was highly controversial when it was first suggested 5 years ago. People said, oh, quantum mechanics in hot, wet stuff like, plants or us or whatever. Surely not. But these things are actually pretty small. These molecules are sort of tens of nanometers, hundreds of nanometers size. And they're held in place by a very rigid protein scaffolding. So they're not just a great lump of junk. All these little chromophores are all lined up and held in place exactly where they should be by this vibrating protein scaffold. So they're not just sort of thrown together in a sort of like soup. They've been carefully constructed, by evolution of course, to exploit the fact that there is a quantum mechanism that they can use to get energy faster through to the reaction centre. So that's a really interesting idea. So let me just say a few words about a classical random walk. So the basic idea is I start at one site and I toss a coin. If it's heads, I go that way. If it's tails, I go that way. Then I toss it again and so on. But the interesting thing about a quantum random walk is at the very first step, I go both ways simultaneously. Remember, it's a superposition. So that's fine. Now I'm there and there. But the next step, this one goes over here, this one goes here, but this one comes back on top of it. And not surprisingly, there's a complete cancellation of that probability amplitude. So in fact, that event never happens. So it never comes back to where it starts. It keeps going out. And that sounds pretty good. That sounds like you might be able to get home a lot faster than if you keep coming back to where you start, staggering around in the dark all the time. And so that's the trick for quantum transport. So instead of having ordinary diffusive transport, we can have, which just sort of diffuses away, the root mean square position goes linearly with time. With this quantum cancellation wiping out things in the middle, I can get much, much faster. I can get something that goes as time squared. So it goes racing out to the sides. It's very, very fast. Now, it's a little bit more complicated than that because what's actually going on in these things, as I said, they're held in a protein cage. So as the protein cage distorts, it's stretching the chromophores and shrinking them just right, which is changing their energy level structure. So not only is this thing doing quantum hopping, it's kind of surfing on the vibrational motion of the whole protein cage. And that's truly remarkable. And one of the standard examples is the so-called FMO complex, which is like a little quantum wire that takes some optical energy up here and sends it through to where the reaction centre is. And it's this arrangement of dipoles, and people have actually worked out how strongly they're coupled. You can actually work out what's the most, this is like working out the reflectivity and transmittivity of beam splitters, figuring out how that one will go to there and how that one can go back and go to there and that one can go there, there and there. So they've worked out all of those probability amplitudes doing careful spectroscopy, and they can model it exquisitely, and they can include the molecular vibrations, and sure enough, it reproduces what the experiment says, that there's this macroscopic, not that macroscopic, but at least it's a big molecule, it's not a single hydrogen atom, where this energy is being coherently propagated across the reaction centre, across the whole antenna towards the reaction centre. So that's all very interesting, and people are now doing these experiments at room temperature and they work just fine. But okay, so it took 3 billion years for life to figure that out. But now that we know it, can we take that idea and use it to engineer artificial photosynthesis? Won't be cheap, or perhaps even something more interesting, which is energy harvesting. So one of the things we're exploiting in our centre is to use this idea of improving the efficiency of energy transfer to build devices that will harvest energy from the ambient environment. It could be optical, like photosynthesis, but it could just as well be ambient vibrations. Just walking along, every time you hit the ground, your body vibrates. If you could sort of harvest that energy and use it in a circuit, you could charge your mobile phone without ever having to worry about plugging it into the circuit each night. You just walk around and it will just charge just by ordinary vibrations. So that's what we're trying to do. So here's one way to do it. We build one of these mechanical resonators, a big long beam that can just vibrate up and down. Then we put inside there some quantum dots, like Professor Riley talked about, gallium arsenide quantum dots. And as the beam flexes, it changes the size of these dots, and the energy can then surf along from one dot to the other, from this side to this side, very, very much more efficiently than it would if it just had to hop. If it's just hopping diffusively, it mostly doesn't go anywhere, just slowly diffuses out. But if we get this vibrational electronic coupling just right, we can have it so that it surfs straight through from one side to the other. And if we do it right, we can suck out vibrational energy. So I'll just refer you to this very nice paper by Luca Gamartoni called "There's Plenty of Energy at the Bottom." That is, you've probably heard something like this title somewhere before, right? But there's plenty of energy at the bottom. That is just down there, just thermal motion. If we can just suck it up and use it, you might think, well, it's going to violate the laws of thermodynamics, but these are not closed systems. Sun comes up, sun goes down. Gets hot, gets cold, gets hot, gets cold. So you can harvest just the thermal changes to power small sensors and small mobile phones. In fact, if you do the numbers, you find it would be relatively easy to power a wireless sensor network. You only need, if we're down here at the size of a quartz oscillator, little tiny clocks, you only need 100 nanowatts. You wouldn't need much of an improvement in efficiency to power those devices. So, this would have all sorts of interesting applications. We could build RF radio frequency sensors for the human body that you wouldn't need to replace the batteries. They would just charge themselves just from ambient energy. You could build little tiny little millimeter-sized sensors that you could just throw out into the forest to monitor forest fires or monitor carbon dioxide or pollutants and so on. You don't have to run out and change the batteries in a million of these things every few weeks. They just power themselves. So there's quite a big market for coming up with clever ways to harvest energy like this. And the key difficulty in doing it is transport. If you have small devices that are naturally a bit messy, it's hard to make sure that the vibrational energy goes to the place where it's supposed to do the stuff through the capacitor or the battery or the chemical reaction that you're using to charge the battery. So I think that will be one of the more immediate examples of quantum-enabled technology that will come out of our ability to engineer fairly large systems at the quantum level. Quantum computing will come, but not for a little while yet, but because of the effort that's gone into quantum computing, we now have the technological capability to think about these other sorts of things that will be of more immediate feasibility and of considerable use. So with that I'll finish. So we've just seen how strange the quantum world is, but let's not stop there, right? It's strange, okay, let's just get over that. That's the way the world is. Let's just figure out how to engineer the world at the quantum level and build powerful new technologies. So essentially taking Schrödinger's partial differential equation, which I've taken the liberty to put here, I hope it's not too terrifying. I didn't put up Maxwell's equations, but I thought I should at least put up Schrödinger's equation, which he got by thinking about atoms. But what we want to do is build quantum circuits, quantum resonators, quantum mechanical devices that operate anywhere between the micron scale all the way up to the kilogram meter scale, fully quantum mechanically, to solve useful technological problems. So thank you very much.